Hello everyone, my name is Aditya and today I'll be walking you through a topic that sits right at the heart of digital signal processing. It's called aliasing. Now if you have ever heard of that word before, your first instinct might be to think of it as a problem, something that needs to be fixed, something that engineers spend a lot of time trying to get rid of, and historically that was absolutely the case. But what I want to show you today is that aliasing is actually far more interesting than that. It's not just an error that needs to be avoided. It's structured, predictable, and in many cases deliberately engineered phenomenon that power some of the most important technologies in modern signal processing. By the end of this video, you'll understand what aliasing is from principle and how it shows up in frequency analysis and many more applications. What is aliasing? Let's start with the most basic question. What is aliasing? At its core, aliasing is what happens when you try to represent a signal using sampling rate that's too low relative to the frequencies present in that signal. Think about it this way: when we work with real world signals, audio, radio waves and sensor data, these signals exist in continuous time. They vary smoothly and vary continuously from one moment to the next. But digital signals can't store and process continuous signals directly. They need to take snapshots of the signal at discrete points in time. This process is called sampling. Now here is where things get interesting. If you sample a signal frequently enough, you can perfectly reconstruct the original from these discrete snapshots. This is guaranteed by the Nyquist theorem, which tells us that to perfectly reconstruct a signal, your sampling rate must be at least twice the highest frequency present in that signal. But what happens when you don't meet that condition? What if you're sampling too slowly? Then something strange and almost counterintuitive happens. Two completely different frequencies can produce the exact same set of values, and they become indistinguishable from each other. One frequency pretends to be the other. This is called aliasing. The word itself comes from the idea that one frequency is under the alias of another. It shows up as a ghost or a false frequency in your digital representation that wasn't actually there in the original signal. This might sound like a purely negative thing, and in many traditional contexts it was treated that way. But as we'll see, understanding the structure of aliasing is what allows engineers to do some truly clever things with it. Sampling in the frequency domain. To really understand aliasing, we need to look at it from the frequency domain perspective, because that's where its true nature becomes visible. When you sample a continuous time signal, you essentially multiply it by a train of impulses, spikes that occur at regular intervals of time and are separated by the sampling period t. In the time domain, that multiplication is straightforward to understand, but in frequency domain, multiplication in time corresponds to convolution with the spectrum of the impulse train. And here is a key insight. A Fourier transform of an impulse train is itself an impulse train, but in the frequency domain. This means that when you sample a signal, its frequency spectrum gets replicated at integer multiples of the sampling frequency. You don't just get one copy of the spectrum, you get infinite many copies spaced apart by the sampling rate. Now, as long as your sampling rate is high enough, these spectral copies stay separated from each other. They don't overlap. And if they don't overlap, you can use simple low-pass filters to isolate the original spectrum and perfectly reconstruct your signal. But if the sampling rate is too high, too low, you have violated the Nyquist condition and those spectral copies start to overlap. You can no longer just separate them. The frequency from one copy bleeds into the frequency of another, creating a jumbled, distorted version of the original spectrum. This overlap is aliasing, seen directly in the frequency domain. So frequency isn't just some mathematical curiosity. It has a very concrete visual signature called spectral overlap. And understanding where that overlap happens is the first step to understand how to control or exploit this. So is it really a bad thing? Now we understand that what aliasing is, let's ask the question that the entire presentation is built around. The traditional view of aliasing going back decades was very clear. Aliasing equals distortion. It corrupts your signal, it introduces frequencies that weren't there, and it ruins the accuracy of your digital representation. The solution was simple in principle. Use anti-aliasing filter before your analog to digital converter to remove all frequency content above the Nyquist limit. This was standard practice, and it's still necessary in many situations today. But in modern DSP view, it's quite different and far more nuanced. Yes, aliasing can cause distortion, but here's what's also true. Aliasing is predictable. Because it's governed entirely by the laws of mathematics, specifically the mathematics of sampling and spectral replication, you can calculate exactly where the alias components will appear in the spectrum. You know which original frequencies will map to which alias frequencies, and because it's predictable, it can be controlled. If you really know what aliasing will occur, you can design your system so that aliasing either doesn't matter or can be compensated for. And even more powerful, because it's controlled, it can be cancelled. In some systems, aliasing is deliberately introduced in multiple stages, and the aliasing components from one stage are arranged to cancel out the aliasing components from the other. This result is perfectly clean signal, even though aliasing was occurring internally throughout the process. And finally, this is the most exciting part, aliasing can be exploited. Engineers have designed entire technologies that only work because of aliasing. They use aliasing as a tool rather than fighting against it. Aliasing in multi-rate DSP. Our first topic is aliasing in multi-rate digital signal processing, or multi-rate DSP. The word multi-rate simply means that a system operates at more than one sampling rate simultaneously, or changes the sampling rate of a signal during processing. This is an incredibly common requirement in real-world systems. Think about audio processing software that needs to handle signals originally recorded at different sample rates, or a communication system that processes signals at high bandwidth but then saves storage space by working at a lower rate internally. There are two fundamental operations in multi-rate DSP: downsampling, which reduces the sampling rate, and upsampling, which increases it. Both of these operations have direct relationships with aliasing, and understanding these relationships is essential. Downsampling. Let's start with downsampling, which is also called decimation. Downsampling by a factor m means you keep only every mth sample and throw the rest away. So if you have a signal sampled at 8,000 samples per second, and you sample the signal at 4,000 samples per second, you effectively cut out your data rate in half. Now think about what this does in frequency domain. Your original sampling rate was high enough to represent frequencies up to some Nyquist limit. When you downsample by a factor m, you are reducing the effective sampling rate by a factor of m. This means that the new Nyquist limit is also reduced by a factor of m. What happens to the spectral copies that were sitting up there at the high frequencies? They get compressed into the lower frequency range. And if any of your signal's frequency content was above the new lower frequency Nyquist limit, then those components will now alias. They fall back and appear as lower frequencies. That's why in practice you almost always apply a low pass filter before downsampling. This filter removes all the high frequency components above the new Nyquist limit, preventing aliasing. The combination of this anti-aliasing filter followed by sampling is called decimation. The key point here being that downsampling is inherently an alias generating operation. Whether that alias is harmful or useful depends entirely on how the system is designed. Controlled aliasing. This brings us to the concept of controlled aliasing. The idea that if we know what exactly the aliasing will be, we can design our system to make that aliasing harmless or even beneficial. Controlled aliasing is not about being sloppy or careless. It's about having a precise mathematical understanding of what happens to a signal when you downsample it, and then designing the rest of your system to have a processing chain that accounts for that. For example, suppose you have a signal that contains multiple frequency bands and you only care about one of those bands. If the band you care about is in a range that won't alias when you downsample, and the bands that you don't care about won't alias into your region of interest, then you can safely downsample and still get the information you need without any aliasing filter. The aliasing is there, but it just doesn't affect what you are measuring. This kind of thinking, being deliberate about what aliasing occurs and where it doesn't, is a hallmark of modern multi-rate DSP design. And instead of reflexively filtering everything, engineers analyze spectral content of the signal and make intelligent design decisions about whether the aliasing can be tolerated, when it needs to be prevented, and when it can be actually put to use. Why is downsampling useful? Let's talk about the practical advantages and applications. The most obvious advantage is the reduced computational cost. If you are running a digital filter on your signal, every sample requires a set of multiplications and additions. Cut your sample rate in half and you approximately half your computational load. In real-time systems, embedded processors, hardware accelerators, software radio platforms, this can be the difference between design that works and one that doesn't. Closely related is the reduced memory usage. Fewer samples mean less data to store. In streaming systems that buffer signal data, or in applications that record audio or sensor data over long periods, this directly translates to storage savings. And naturally, with fewer computations and less data, you get faster DSP processing overall. Your system can respond more quickly to changes in the signal and may be able to run multiple processing chains simultaneously that would otherwise be too expensive. The applications of downsampling are everywhere. Even in audio compression, think about MP3, AAC and other formats. In these formats, the signals are processed at reduced rates internally to reduce the amount of data that needs to be encoded. In image processing, downsampling is used to create lower resolution versions of images for display or storage. In communications receivers, signals from the antenna are often brought to a lower sampling rate as quickly as possible to reduce the load on downstream processing. And in multi-rate systems of all kinds, the ability to move between different sampling rates is a core tool in the engineer's arsenal. Filter banks and aliasing cancellation. Now let's move into one of the most elegant applications of controlled aliasing. Filter banks and aliasing cancellation. Filter banks are systems that split signal into multiple frequency subbands and process each subband separately. It then recombines them. You encounter filter band technology every time you listen to MP3 audio or use a voice codec on a phone, or even open a JPEG image. They're everywhere in signal processing. The reason filter banks are so relevant to aliasing is that they inherently involve downsampling, which, as we discuss, involves aliasing. The challenge and the beauty of the filter bank design is in arranging the things so that the aliasing introduced by one stage cancels out the aliasing from another stage, giving you clean, artifact-free output. So let's take an example of a two-channel filter bank. The idea is this: you take your input signal and pass it through two filters, a low-pass filter and a high-pass filter. Together, they divide the frequency spectrum into two halves. After filtering, you downsample each branch by a factor of 2. Now you have two signals, each at half the original sampling rate, representing the low frequency and the high frequency content of your original signal respectively. After you've done whatever processing you want to on these two subband signals, you want to reconstruct the original signal. To do this, you upsample each branch back up by a factor of 2 and pass them through a synthesis filter and add the results together. Now here is the aliasing problem. When you downsample the filtered signals by 2, aliasing occurs. The spectral copies fold back on top of each other, and then when you upsample and add the branches back together, you might expect to hear terrible distortion because aliasing was introduced in both branches. But here's the key insight of the two-channel filter bank. If you choose your analysis and synthesis filters carefully, specifically if they satisfy certain mathematical relations, then the aliasing introduced in the downsampling step of one branch will be exactly cancelled by the aliasing in the other branch when you add them together in the reconstruction stage. The aliasing doesn't disappear, it gets cancelled. And this cancellation can be made exact, not just approximate. That is the magic of the filter bank. So what are these aliasing components? To understand how this cancellation works mathematically, let's look at what happens to the signal in the frequency domain. When you downsample a signal by 2, the output spectrum contains of two terms: the original spectrum scaled and frequency compressed, plus an aliasing component, the spectrum that has been shifted by half the sampling frequency and added on top. This aliasing component is the contamination introduced by downsampling. In a naive system, this extra term would remain in the reconstructed output and show up as distortion. But in a filter bank, both the low pass branch and the high pass branch both introduce their own aliasing components, and these components are related to each other through the filter frequency responses. And these filters are designed specifically so that when you add the two branches together after upsampling, the aliasing component of the low pass branch and the aliasing component of the high pass branch are equal in magnitude but opposite in sign. So they cancel out. What remains after the cancellation is only the desired signal, that is the output, and that is possibly delayed or slightly scaled input, but free of any aliasing artifacts. This is a profound result. Aliasing is not avoided, but it's deliberately introduced and cancelled by design. The entire architecture of the filter bank is built around this careful management of aliasing. Applications of filter banks. Filter banks and aliasing cancellation that they depend on show up in an enormous range of practical applications. MP3 compression uses filter bank called the modified discrete cosine transform to split audio into frequency subbands. Each subband is compressed separately according to psychoacoustic models, and the frequency bank includes aliasing during this process. But this synthesis filter bank at the decoder cancels it out. Subband coding. In this, it's a technique in which the signal is divided into frequency bands, each of which is encoded or processed independently. Telephone codecs, video codecs, and speech enhancement systems all use this approach. Wavelet transform. This is a generalization of the filter bank concept. Rather than using the fixed bandwidth subbands, wavelets use subbands that are geometrically spaced, which matches the way many natural signals behave. The mathematics of perfect reconstruction wavelets is directly connected to the filter bank aliasing cancellation theory we've been discussing. Image compression, specifically the JPEG 2000 standard, uses a two-dimensional wavelet transform built on exactly these principles. Every time you view a JPEG 2000 image, you are benefiting from aliasing cancellation in multiple dimensions simultaneously. In all of these cases, aliasing is not an accident or an unavoidable evil. It's intentionally created and then intentionally cancelled, a controlled phenomenon that makes the entire system work. RF undersampling. Now let's shift gears and talk about one of the most practical, powerful applications of deliberate aliasing, RF undersampling. It's also called bandpass sampling. When aliasing transitions from being mathematical curiosity to being a genuine engineering tool, that has transformed how we design wireless receivers and software-defined radio systems. Bandpass sampling concept. The traditional approach to receiving a radio frequency signal is to use an analog mixer, a hardware component that shifts signal from its carrier frequency down to a lower baseband frequency. This mixing process involves multiplying the incoming signal by local oscillator, which produces some and different frequencies. Difference frequencies, that is the baseband signal, is what you actually want. Mixers are relatively complex, require precise local oscillator frequency synthesis, and consume analog hardware resources. They also introduce their own noise and non-linearity issues. Bandpass sampling offers a clear alternative based on aliasing. Here's the key idea. Suppose your signal of interest is a bandpass signal, meaning it's concentrated in a relatively low frequency band centered somewhere around a higher carrier frequency. The actual information bandwidth of the signal might be quite small, even though the carrier frequency is actually high. The Nyquist theorem tells us that the sampling rate must be twice the highest frequency, but this is actually a sufficient condition for our baseband signals. For bandpass signals, there is a more nuanced result. You only need to sample at twice the bandwidth of the signal, not twice the carrier frequency. This is because the bandpass signals have most of their energy in the narrow band. When you sample a bandpass signal at a lower rate than the carrier frequency but still adequate for the signal's bandwidth, the result aliasing deliberately shifts the signal down in frequency, effectively performing the same function as an analog mixer but without the mixer hardware. The alias copy of your signal lands at a lower, more convenient frequency where you can process it digitally. This is the essence of bandpass sampling or RF sampling, RF undersampling, using aliasing as a frequency translation mechanism rather than fighting it. Let's make this concrete with a numerical example. Suppose you have an RF signal centered at a carrier frequency of 70 MHz and the signal has a bandwidth of 10 MHz. So it occupies frequency from 65 MHz to 75 MHz. The naive Nyquist carrier would say that you need to sample at a rate of more than 150 MHz to avoid aliasing. This is very high speed analog digital to converter and it's very expensive and power hungry. But with bandpass sampling you can do much better. If you choose a sampling frequency of let's say 30 MHz, then when you sample the 70 MHz signal, the aliasing places a copy of the signal spectrum at a location determined by the 70 MHz modulo 30 MHz, and calculating gives us 70 divided by 30, which gives us 2 with a remainder of 10. So the alias copy lands at 10 MHz, right in the middle of a range that's easy to handle digitally. Your 10 MHz bandwidth signal, originally at 70 MHz, has been down converted to sit at around 10 MHz. Just by choosing the right sampling rate and letting aliasing do the frequency transmission, you've eliminated the need for an analog mixer entirely. Of course, this only works if you're clean and careful about the spectral arrangement. You need to make sure that the alias copy lands in a clear, unoccupied region of the baseband spectrum and need to ensure that the other interfering signals don't alias into the same region. Why RF sampling is powerful? Let's talk about how this matters practically. The most significant advantage is that no analog mixture is required. Traditional super heterodyne receivers, the kind that have dominated radio design for nearly a century, require at least one mixing stage, often several. Each mixer needs a local oscillator, a bandpass filter and a careful impedance matching. By replacing the mixer with bandpass sampling, you dramatically simplify the analog front end of the receiver. This leads to a reduced hardware complexity. Fewer components means a smaller circuit board and fewer potential points of failure. It also leads to lower cost ADC design in many cases. While a very high frequency ADC would be expensive, a moderate rate ADC running at the bandpass sampling frequency is often cheaper and more power efficient than the combination of a mixer plus a lower rate ADC. The applications of this technique include software-defined radio systems, platforms where most of the radio's functionality is implemented in software rather than bandpass sampling. An SDR can be reconfigured at different frequency bands and modulation schemes purely through software changes without touching the hardware. Modern RF receivers in cellular base stations, satellite ground stations and radar systems increasingly use variations of bandpass sampling to achieve performance and flexibility that would be impossible or impractical with purely analog down conversion. The bottom line, aliasing acts as a frequency translator. And in the world of RF systems, this transforms what was once a bug into a feature of fundamental importance. Aliasing and FFT based convolution. Our final major topic is aliasing and FFT based convolution. This takes us into a slightly different domain, not sampling in time but rather the mathematics of how we compute convolution efficiently using the fast Fourier transform. This topic is important because it shows aliasing is not just a phenomenon of sampling process, but it's a structural property that appears whenever you work with periodic or finite length signals in the frequency domain. Circular convolution. To understand aliasing in FFT, we first need FFT convolution. We first need to understand circular convolution. When you compute a convolution, the fundamental operation of filtering in this DSP, you're sliding one signal past another and computing the area of overlap at each point. This is called linear convolution, and this is what you want when filtering. The FFT gives you a very fast way to compute convolution, but that's the catch. FFT implicitly assumes that the signal is periodic and that the finite block of samples that you're processing repeats over and over infinitely in both directions. This is a mathematical convenience that makes the FFT work, but it has a consequence. When you multiply two FFTs together and take the inverse FFT, what you're actually computing is circular convolution, not linear convolution. In circular convolution, the output wraps around and contributes that would have had fallen off at the end of the block are wrapped back at the beginning. This is directly analogous to aliasing in the time domain. Just as aliasing in the sampling causes high frequency components to wrap around the lower frequency range, circular convolution causes the time domain output to wrap around within the block length. Visually, if you imagine rolling your signal lattice into a cylinder and computing the convolution around a circle, that's exactly what circular convolution is. The edges of your block aren't edges, they're at the same point. Time domain aliasing interpretation. The connection to aliasing becomes explicit when we look at what happens at the time domain when you do FFT processing with insufficient block length. Suppose you have a signal of length L and you convolve it with a filter of length M. The true linear convolution result has length L plus M minus 1. But if your FFT block size is smaller than this, the circular convolution wraps around and the extra output samples from the end of the block fold back and add on top of the top of the beginning of the block. This is exactly time domain aliasing. Time domain equivalent of spectral aliasing. Just as aliasing in the frequency domain is caused by spectral copies overlapping due to insufficient sampling rate, time domain aliasing is caused by the periodic extension of finite block overlapping with itself due to insufficient block length. The solution is straightforward. Make your FFT block size large enough so that the circular convolution result has room to hold the full linear convolution without wrapping. This is achieved by zero padding. Appending zeros to your signal block before computing the FFT. With sufficient zero padding, the circular convolution result is identical to the linear convolution result. The aliasing is prevented by ensuring there is no overlap between periodic outputs, periodic copies of the time domain signal. Overlap and add method. This is a practical technique for computing convolution of very long signals using FFTs. It's designed specifically to avoid the time domain aliasing. Here's how it works. The long input signal is divided into shorter blocks. For each block you choose an FFT size n that's at least Lx plus Lh minus 1, where Lx is the block length and Lh is the length of the filter impulse response system. Then you zero pad both the input block and the filter to length n, capital N. You compute the FFT of both and multiply both of them together in the frequency domain and take the inverse FFT to get the convolution result for that block. Because we have zero padded the right length, the circular convolution is identical to linear convolution and no aliasing occurs. But there is another subtlety. Consecutive blocks of convolution results overlap with each other. Each block's output is longer than the input block, so it extends into the region of the next block. The overlap add method handles this by keeping track of the tail from each block and adding it to the beginning of the next block's output. The result is a perfectly correct linear convolution of the full long signal with the filter computed efficiently using FFTs without any time domain aliasing. The zero padding is a critical step. Without it, circular aliasing would corrupt the result, and with it you get an efficient aliasing free computation. So aliasing is a structural property. We have now seen that aliasing is in three very different contexts: downsampling, filter banks and FFT convolution. Let's take a step back and recognize something important. Aliasing is a structural property of discrete time signal theory, not a special case or an exception. It appears because sampling, which creates a spectral replication. It appears because of downsampling, which creates the spectrum, which compresses the spectrum and causes those replicas to overlap. It appears because of circular convolution, which implicitly assumes periodicity and causes time domain wraparound. And it appears because of the FFT itself, which assumes that any block of samples is an infinite periodic signal. In each of these cases, aliasing is not a bug in the mathematics. It's a direct consequence of the mathematical framework that we use to represent and process discrete time signals. It's built in the very structure of digital signal processing. This is a profound observation because it means aliasing is unavoidable at fundamental level and you cannot eliminate it by being more careful or using better hardware. What you can do is understand it, predict it and design your system to either prevent it when necessary or harness it when advantageous. Unified view of aliasing. Let's now put everything together into a unified view of aliasing. From a mathematical standpoint, aliasing can be understood as spectral folding. High frequency components fold back into the lower frequency range due to inefficient sampling rate or block size. It can also be understood as time domain wraparound in finite length processing with FFT. It is a signal period extension artifact, and the mathematics of DFT and FFT impose periodicity on signals, and this periodicity can interfere with the signal itself if boundaries aren't handled correctly. Most fundamental aliasing is deterministic interference. Unlike noise, Unlike noise, which is mostly random and unpredictable, aliasing is completely determined by frequencies involved and the sampling rate or block size used. You can calculate exactly what it will do, and that determinism is what makes it possible for us to control and exploit it. As we have seen, engineered uses of aliasing are substantial. Multi-rate systems use downsampling and upsampling to perform efficient signal processing at different data rates. Filter banks use deliberate aliasing and cancellation to achieve perfect signal reconstruction after sub-band processing. RF undersampling uses aliasing as a frequency translation mechanism to eliminate the need for analog mixers. FFT convolution methods must carefully manage time domain aliasing through zero padding and achieve correct results. Aliasing is everywhere in DSP. Understanding it deeply gives you fundamentally richer ability to design and analyze signal processing systems. So let me close with the key takeaways from everything we have covered today. Aliasing is not random distortion. It may look like random noise when you first encounter it without understanding, but it's not random in any sense. It's entirely mathematical, and given the sampling rate and signal frequencies, you can predict exactly what aliasing will produce. It's structured, predictable, spectral folding, and that is its defining characteristic. The aliasing components appear at specific calculable frequencies, and their amplitudes and phases are determined by the original signal. Nothing about aliasing is left to chance. Modern DSP engineers design with aliasing, not against it. This is the shift in perspective that this entire presentation has been building towards. Aliasing is a tool. It can be cancelled, controlled, and exploited. The filter banks in your music streaming app, bandpass sampling in your software radio, and the zero padding in your digital filter implementation, all of these reflect a deep understanding and careful management of aliasing. The engineers who build these systems don't eliminate aliasing. They understand it so well that they can use it to their advantage. That is the real reason here. That is the real lesson here. In signal processing, as in many fields of engineering, the phenomena you don't understand are the ones that defeat you, and the phenomena you understand deeply become your most powerful tools. Thank you for watching, and I hope this has given you a new appreciation for aliasing, not as an enemy to be feared, but as a fundamental and fascinating property of the digital world that, when understood, opens up an extraordinary range of engineering possibilities. Thank you.